All right, for section 5.2, we're going to continue talking about log functions, except we're going to introduce integration with them. Okay, so as I'd mentioned, in section 5.1, that the derivative of the natural log of x was just 1 over x. So for the integration side, well, the integral of 1 over x dx is the natural log of x plus c. Okay. Notice I did put this x in absolute values. That is because the natural log of a negative is undefined. So we have to ensure that our x is positive. Once we know that the x can only be positive, then we can drop that, and I'll show you what I'm talking about in just a bit. All right. And then if we have something that's not x, but we just have, some kind of term, u, or so it could be like x squared plus 1, etc., then we can just say, well, that's the natural log of u plus c. Okay. All right, so let's go ahead and do an example. Let's say that we have, let's say we want to find the indefinite integral of 3 over x dx. Okay. Well, then I can pull that 3 out front and say, well, that's 1 over x dx. Well, as we've already mentioned, the natural log is the integral of 1 over x, so that we have 3 times the natural log of x plus c. Okay. All right, but however, just to make a note of this, because of the power rules, or the log rules that we do have, we could rewrite this as the natural log of x cubed plus c. Okay. As far as those answers, there's no difference for me, but you could condense that if you wanted to. And then you have to keep the absolute value because x cubed could be negative. Okay. All right. So now let's do another example. Let's say that we have 1 over 5x minus 1 dx. Okay. So this would be a time that we would need to use UDU substitution. So let's go ahead and choose our u to be 5x minus 1. Okay. So then that makes du be 5 dx. Okay. Well, I don't have a 5 that I can replace, so I'm going to divide this 5 over and say, well, that's 1/5 du is equal to dx. Okay. So now I'm going to replace my dx, and then I am going to have my 5x minus 1 to be u. Okay, so I'm replacing dx with 1/5 du. So that's why I can do this and say, well, that's just 1 over u now, du. All right, I replaced dx with 1/5 du, so there's my 1/5, there's my du. Well, so that is 1/5 the natural log of u plus c. But as we know, the u is actually equal to 5x minus 1, so we really have 1/5 the natural log of 5x minus 1 plus c. Okay. So that would be the final answer for that one using UDU substitution. Okay. All right. So now let's look at another example. And let's use it to find the area. Since integrals are all about finding area, let's find the area of the region there we go, of the region bounded by, let's say y is equal to x over x squared plus 1. X equals 0 and x equals 3. Okay, so I don't have to graph this or anything to be able to know what I'm looking at. All right, but just in the event that we wanted to, we could look at this and go, okay, well, x0 is here. Well, okay, x is 3 is somewhere over here. All right, and then you can use Desmos or some kind of graphing tool, your graphing calculator, and look at the graph of x over x squared plus 1 if you wanted to. You don't have to, but I'm going to show you what it looks like just so you kind of have an idea. Yeah. So the graph looks something like this. Okay? And we're only going to try to find the area that's right here. Okay? All right, how we do that is by invoking an integral with limits of 0 and 3 with the function x over x squared plus 1. So let's say that our area is equal to, from 0 to 3, of x over x squared plus 1 dx. Okay, again, I have to use u/du substitution to solve this, so I'm going to choose my u to be x squared plus 1. Okay. So then du is 2x dx. So I do have this x here that I can replace and the dx, so I'm just going to move the 2 over and say, well, this is 1/2 du is equal to x dx. So now I'm going to replace my x dx with 1/2 du. So I have the integral of 0 to 3 of 1 over u times 1/2 du. I can pull that 1/2 out because it does not affect the integral, so I really have 1 over u du. Okay. All right, so now I know that the integral of 1 over u is natural log, so I have 1/2 I have natural log of u, and I am going to evaluate this from 3 to 0. Okay, so I have 1/2. The natural log u is actually x squared plus 1, and x squared plus 1 could never be negative. So I have x squared plus 1 from 3 to 0. Okay, and I use this little notation here, this bar, to just denote that I'm going to evaluate this, and my limits are 3 to 0. So that's just a notation thing for me. Okay, all right, and so I say, well, that's 1/2 natural log of 3 squared plus 1 minus the natural log of 0 plus 1. Okay. Well, 3 squared plus 1 is 9, so I have the natural log of 10. Excuse me, 3 squared is 9 plus 1 is 10. And then 0 plus 1 is 1. The natural log of 1 is 0. Okay. So then my final answer is 1/2 the natural log of 10. So that would be the area that is bounded under this curve from the drawing. Okay, so that's how we can use integration with logs to formulate an area. Okay. All right, so let's look at another example. See if this works when I did this. Showing that there should be a page there. Okay. All right, so now let's look at an example where we may have to not only do a log, but we may have to do some other simplification stuff. So let's try to find the indefinite integral of x squared plus x plus 1 over x squared plus 1. Okay, and this is all with respect to x. Okay, so here's another just integration trick that you can use. So we can use long division when we have something like this. Before we integrate, when the degree, so the power, so when the degree, so the power of the highest power in the numerator and denominator, when the degree of the numerator is greater than or equal to the degree of the denominator. So the degree for this one, the degree for the numerator is 2. The degree for the denominator is also 2. So we can simplify this using long division. Okay. This is just another one of those tricks that can help us out. Okay. Okay, so now we can use long division to simplify this, to say, well, this is x, so we're saying x squared plus 1 is going to divide x squared plus x plus 1. Okay, so just using it the same way as what you see up, x squared plus x plus 1 divided by x squared plus 1. That's all I have rewritten. All right, and I have an x squared in my inside the divisor or the dividend, and a 1, and then I have x squared plus 1 out here. So it works the same as you did long division in, say, 3rd or 4th grade. All right, so it goes in one time. I multiply it, so I can subtract off x squared, and it can subtract off 1. All right, so that only leaves me with this x. Okay. But I have the remainder of 1 times x squared plus 1. Okay, so now I can't divide x by x squared plus 1. Okay, but I still have to accumulate this 1. So what I'm really saying is I have 1 plus x over x squared plus 1. Okay, so and just think about this, right? Like, and how this came about. Okay, well, 101 is the equivalent of x squared plus 1 over x squared plus 1. So if I added those together, then I would have x squared plus 1 plus x, which is the original. So nothing changed, but now I can do the integral. Okay, so I'm going to take the integral of this with respect to x. All right. Well, according to fundamental theorem of calculus, I can do the integral of this and this separately. Okay. Well, the integral of 1 is easy because it's just x. Okay. All right. This one, though, the second term is going to require u du substitution. So I'm going to let my u be x squared plus 1. I'm going to let du then be 2x dx. Of course, I want to divide my 2 over, so I have 1/2 du is equal to x dx, because I can replace x and dx. All right, so that actually leaves me with 1/2. Oh, this is me doing the integral, sorry. There we go. So I have 1/2. I have 1 over u du. Well, I do the integral of that, and I can say, well, this is 1/2 the natural log of u plus c, and u is x squared plus 1. So I can say, well, this is x plus 1/2 the natural log of x squared plus 1 plus c. Okay. So the long division part of that was just another tip or trick to be able to simplify our our function before we integrate it, and then I used UDU substitution and natural log to be able to find the integral. Okay. So now let's look at some integrals of trig functions. Okay. All right. So, there we go. So integral of trig functions. Okay. All right. And so let's just look at one, and then I'm going to give you a list of all of them. Okay. So let's say that we want to find the integral of the tangent of x with respect to x. Okay. Well, tangent of x, if you remember from pre-calc, maybe even calc 1, tangent of x is really the sine of x over the cosine of x with respect to x, right? Well, how could I integrate this? Well, I've got cosines and sines, so maybe I could use something like u du. So I've got u. I'm going to let my u be cosine of x because I know that the derivative of cosine is sine. All right. So I'm going to say u is the cosine of x. So then that means du would be the negative sine of x. All right. So the derivative of cosine is negative sine. Well, I've got a sine of x that I can replace, but I need to do something with this negative, so I'm going to move it over and say negative du sine of x, and there should have been a dx attached right there. Okay. Now I can replace my sine x dx with my negative du and say, well, this is the negative 1 over my u du. Okay. So I replace sine x dx with negative du, and then I replace cosine of x with u. I can integrate this to say, well, that's the negative natural log of u, and I'm going to have to use absolute values, plus c. Okay. And so now I'll just replace u and say, well, the negative natural log of cosine of x plus c. All right. And so the same kind of logic can be used to generate all of the trig functions, okay? But I'm just going to show you what they are. So the integrals of the trig functions, and these are the 6 basic ones. So we have the integral of sine, and I'm going to use u instead of x for these, just so that you know it's like a generic form. If I can get this to erase. There we go. Okay, so I'm going to say that the integral of sine u du is the negative cosine of u plus c. Then we have the cosine of u du is equal to the sine of u plus c. Then we have the tangent. The integral of the tangent with respect to u is, as we just found, the negative natural log of the cosine of u plus c. Then the integral of cotangent with respect to u is the positive natural log of sine u plus c. And then we have secant. So we have secant u du is equal to the natural log of secant u plus tangent u plus c. And then the last one we have is cosecant of u du. And that is the natural log of cosecant u plus cotangent u. Okay? So you can see how close these all are, but these would definitely be something good to just keep in your notes on standby because it's very beneficial and you'll memorize them as you do them. All right, but that ends our lecture for 5.2. So this is just all about integration using logs and some different tips and tricks. If you have any questions, please feel free to email me and have a great rest of your day.